So let me introduce our first speaker. It's Cyber's Chief Technology Officer, Paul Vasiliev. Paul has worked in the industry for over 17 years now, starting with building simple applications and moving on to engineering more complex systems like our company, a 250-person Cybery. Today, Paul will share practices that helped him on his own journey from a junior engineer to a CTO and share how you can break the glass ceiling in your engineering career and level up. Paul, the floor is yours. Welcome.
Yeah, thank you. Hi, everyone. Nice to see you today. Let me open my presentation. As Alicia mentioned, we will talk a little bit about some, in our opinion, useful practices for engineers. We'll be focusing on behavioral practices, so we'll not talk about specific technologies. It doesn't really matter in this context because technology is just a matter of architectural design. So we will talk about how we think good, competent engineers should behave themselves and what you should practice to become one. So first of all, why you should even care about that. So we make this division between coding and engineering, and usually when you are focusing on some specific tasks, like when you have certain functional requirements, let's say you implement those, we consider it coding. So the engineering, when we are talking about the engineering, what we mean is a concern of a person about the full life cycle of any changes they are doing. So for example, if you are creating some feature in some application, as a developer, you're producing the code that works functionally correct. As an engineer, you think about the whole life cycle of this code, how it's built, how it's packaged, how it's delivered, where is it hosted, is it observable, does it provide value, etc. So this is the whole world around the actual coding and development that we call engineering. And so we believe that these practices will probably help you to start moving in that direction, or maybe improving if you're already there. Our hope is that once we finish it, you will have some clearer direction of what to do to improve your competency as an engineer. So first of all, before we cover those, why we should even have any principles, why capture them explicitly. The most important thing, I think, here is that good engineering is based on reasoning, right? So choosing a good technology, producing a great design is not a matter of emotions or just an opinion, uninformed opinion. It's a matter of laying out your assumptions explicitly, laying out the input information you are taking in to design something, and laying out your reasoning on how you produce some technical decisions, architectural ones, etc. And having certain principles, like having a specific design patterns for the code or for the architecture, it makes your reasoning explicit. It's a hard thing to do because when you make a reasoning explicit, you automatically open it to a potential critique for other people, but that's exactly what you want, because when you have your logic and your reasoning explicitly defined, you also open it to improvement by feedback from other people. So that's why it's important to capture not only your decisions, but also to try and capture the assumptions, rules, and the logic of why you made this specific decision. And as a consequence of that, it of course helps you with competency and growth, because when someone challenges your reasoning and your decision, that's the potential point of learning. Better arguments, reasonable arguments, of course, win usually in engineering, and this is an opportunity for either side of these technical arguments to actually grow and learn something new. And of course, these are basically the rules. For example, we are using a lot of those explicit policies and decision rules to build our processes. We invest a lot into into building, as Lisa mentioned, good structured processes of working on software, and having our ideas and our logic explicitly defined very much helps to basically make an inception of certain process and improve it over time and convert it into something more defined. So yeah, a whole lot of reasons of why you should try to capture your decisions in forms of principles or rules explicitly. So that's what we tried to do. We tried to define a couple of these practices that we institutionalize among our teams of engineers, and we believe that they are more or less universally useful, at least enough to share with an outside world. Yeah, let's actually just start going over them. They are not in the order of any priority, they are equally important. So let's start with the first one. When we are working as engineers on some software, it's very easy to fall prey to thinking that software we produce in itself is valuable. In reality, no one cares about software. No one cares about hours we spend as engineers. The value is obviously in solving someone's problems. That's why people come to engineers, basically to somehow improve their lives using the technology. The same analogy, for example, when you come to a doctor to fix some problem with your health, you do not care how much knowledge does the doctor have, or what processes do they follow, etc. What you care about is that they fix your problem. The same, of course, is true for producing software. So people come to us not for the software, they of course come to us to solve some problems. That's why it proved, at least for us, incredibly beneficial to have the most direct link possible between the engineers and we call them problem owners. So people who actually have these problems or needs or new opportunities if it's a new product. So as an engineer, it would be very beneficial to the quality of your work to have this direct link. And basically what it means is removing any unnecessary roles or steps or any communication barriers between you as a person who produces the technology and a person who needs this technology, basically the end user, and someone who needs something to be solved. Fairly simple rules to practice. Well, I would say easy to learn, hard to master. Of course, the very basic practice is always to speak directly with the end users of the software you produce, not with the analyst who potentially writes the requirements for the software, not with the project manager, but directly with people who have these problems and who are users of your software. Of course, if it's a scaled product, you might have, I don't know, thousands of millions of potential users. You would not be able to speak with every person directly. You could use sampling in this case. A lot of software projects are based around some small group, at least, of product owners, and you should strive to speak with these people directly and understand what exactly they need to be solved in their frame of reference, not in frame of reference of the software to be built, but in frame of reference of problem to be solved. And one also related practice here is to try to evaluate the pieces of work you produce as early as possible, because the longer you wait to show something to people you're working for, the higher the chance that you will waste some efforts, because you will have to redo pieces of your work based on the feedback you will receive. So the shorter this cycle of feedback you receive, the smaller the potential waste, which increases the overall efficiency of your engineering process. So show things early, discuss them directly, and iterate quickly, ideally daily, with the end users. This will allow you to produce really good software, where good means solving problems and nothing else. Yeah, it's important to remember that engineering in this regard is not a technical process, it's socio-technical process, which means that we are working not on purely technological systems. This system for us is both technology and people and their behavior and needs. So that's the first one. The first principle is engage the end users of your software directly. The next one, they are related, of course, to each other. So what is it about? People who come to us to build software, of course, are not experts in how the solutions should be structured. They might think about themselves like that, but again, using the healthcare analogy, it would be weird for you to come to some practitioner with your own algorithm of how you should be treated, right? How your case should be handled. Obviously, you rely on the expertise of this person. Unfortunately, in software, this is sometimes the case, and this is okay because sometimes clients indeed have this expertise, but that's a rare case. This means that they are living in problem space. We are living in solution space, and it's our job to convert one map, basically one to another. Which means that it doesn't make sense for engineer to expect that the person who would be coming to them to build software to formulate what exactly needs to be built. They do not know. Even if they think they know, it might be wrong. Might be right, but likely it would be wrong. Which means that it's our responsibility as engineers to actually construct the solution, which means designing the functional behavior of the system. This is some controversial thing, because usually it's a business analyst who produces the requirements, but we came to the conclusion that the most competent person to produce functional requirements is actually the person who would be building those requirements, because functional requirements is the actual design of the system. Once you have the description of the behavior of the system, the next step is just coding exercise. You basically convert one description in one language, in a natural language, into description into more formal language. You do not invent something new here. When you produce the functional description, this is the point in time you actually create the system. It happens there. That's why it's important for engineer to understand how to do that and actually do that. Like take in the problem and design the solution and describe this solution using functional terms, and of course think about non-functional compliance for the system. That's usually we know about as engineers: performance, usability, security of the system, things like that. So the best practice here, I would say, is for you to try and sit down and write functional requirements for the things you are going to produce. It's beneficial for you. It would be beneficial even for the quality of the constructed solution, because writing things down before doing the code will make you think about how the thing that I'm going to be building will behave actually, and capture that. So yeah, that's the second one, is that you are responsible for constructing the solution. Do not expect people to come to you with the description of how solution should look like. They do not know. The third piece, you build it, you run it. So this this principle is about how we structure responsibility. Where does the responsibility of engineer and in terms of life cycle of the software? And here, like a small diagram of how we think about the structure of the team. The classic, I would say, maybe wrong, outdated somewhat way to think about the production team is to think about a step-by-step manufacturing process where you have roles, each role is responsible for a certain step, and you give pieces of work to different roles one by one, like from analyst to developer to tester to DevOps, etc. And each role adds value, and at the end you have a valuable change, for example, to the product. That's, we think, wrong way of thinking about that. So we think as an engineer about an engineer as a central figure in producing this stream of changes to the software, to the technology they are building, and all other roles, they are supporting roles basically for the engineer. By engineer here, we of course mean the whole team, not just a single person, but all other roles, they are here to help you to deliver these changes, to deliver the technology, but it's on you as an engineer to create a technology and push it all the way to the people who will actually use it. Of course, it doesn't mean that you are doing every piece of work. If you need, I know, build CI/CD pipelines to deliver software, of course, most likely DevOps team will be doing it for you. But it's an engineer who should lead and drive what they do, because this person should be concerned with how do I actually deliver this piece of code to the customer, to the end user. And this is true for all other roles. PM supports you in terms of diagnosis of troubleshooting, basically, of the engineering process. Are we on time? Are we within budgets? Are we delivering what's needed? BA helps you to be focused on certain things. So BA knows what to do in terms of the product, what's important, what's not. This is a person that helps you with focus. QA, obviously, diagnostics of the quality of the solution, but also an important piece is actually improving the solution, making suggestions of how to make it better. DevOps, DevOps stuff, everything about the delivery infrastructure, etc. But they're helping you. And it's you who are thinking about the whole life cycle of producing some change. So the practice here, like how to actually do that. When you produce even the smallest change to the code, think about what should happen for this change to actually deliver its value to the end user, how it will be built, packaged, how it will appear in the production environment, how will people access it, how the content will be delivered to them, how will you troubleshoot it in production without having direct route access to servers, etc. So these are all things you should think about to actually deliver the piece of work, and that's what we mean by you build it, you run it. And yeah, this means that there is no separate support team when building the product. The team that built the product actually operates it in production and has the most direct feedback loop of how solution works in production and applies changes to make it better if it's not stable. The next one, it's a more technical one. It's about some characteristics of the systems we produce that we call observability. Basically, why we have bugs in our software. Any bug any defect is a divergence between our expectations, how system and the code works, should work, and how it actually works. Which means that when we have a defect, we didn't know the real state of this system, its real rules and how it behaves. Which means that we lack observability in this. And what we should be striving to do when we are actually designing software is designing it in such a way so that when it operates in some environments, especially in production, we have a good way to understand its state. The bad way would be having access to, I don't know, the database, looking at things on the server, asking for admin level access, etc. A good way would be to build a certain level of telemetry in your product to understand why it behaves the way it behaves, just judging by these measurements, different metrics, logs you output. One very specific thing, when you output an error message to the end user, obviously it's not enough to just throw out 500 code if something goes wrong. You should try to package this message with information that would be actually helpful to user to help you diagnose the problem when they write to support. So things like that, we combine them under a single umbrella of observability. There is a good framework in Amazon Cloud, for example, called Well Architected, that you could reach out for more details about, specifically observability and other related things of how to produce good software. But this was important enough that we felt like it should be a separate principle. And also, I recommend you to take a look at the thing called 12-factor apps. It's a set of 12 principles of designing good apps. So observability is one of the important ones. So when you create any feature, think about how will you observe behavior of this feature in the production. That's your observability for the system. The next one, this should be probably the most familiar to developers. So we should try to do everything as code. This means documentation, tests, infrastructure, CD pipelines, etc. Basically, if you are doing something more than once, you should think about how to do this as a code. The concept of code as code is, of course, obvious to us. Infrastructure is code nowadays as well, but there are many other things you should do as a code. Requirements, even architectural decisions, the designs, etc. It's incredibly beneficial to have an automatic scaled change control by just putting things in Git. So do that. And of course, when you try to convert something in a more formal thing like a code, you basically open up potential automation of this thing in the future, because you basically convert some vague concepts into a more formal definition, which is code. It's a hard thing to do oftentimes, but once you did that, you one step closer to automate this thing. And we believe that as engineers, we should always strive to basically engineer ourselves out of our jobs. So a good outcome for us would be that we built everything and we are not needed anymore, and solution runs fully automatically. So doing everything as code will help you with that. The next principle is about quality. So you probably heard about the concept of shifting things left in the pipeline, talking about security, quality, and anything else. What does it mean? So if you imagine your software production as a pipeline, which has many steps in it. So basically, the earlier you do something in this pipeline, the better. Quality is not the thing that's an added value. It means that you cannot produce bad code, give it to someone to test, for example, and expect that this step of testing in the process will add quality to this code. It will add rework because it will detect issues, give things back to you, and then you will work more on these issues. And basically, any form of post control of anything, security, functional defects, etc., it decreases the efficiency of the overall production process. What increases the efficiency is the author of the job, which is you when you write code. When author understands that it's him or her who is responsible for the actual quality built in the piece of software from the very start. The actual constraints of quality are different, of course, depending on your circumstances. Like you might be building a prototype. It doesn't make sense to spend a year to silver plate the code you're producing, because it will be thrown out in a week. But if you're working on an enterprise solution and many more people for many more years will read your code, not write it, it makes more sense, of course, to spend more time on the code quality. So as an engineer, you should be aware about constraints within which you are designing your software. But within those constraints, you should not ask anyone whether you can do a quality job. You should just do it. And so yeah, if you're asking for a permission from someone, from your manager, for example, to do a good job, something is wrong. You should not be doing that. You should just do a good job, where good is within the constraints you have defined. And as a specific practice to do that, test-driven development and the whole family of continuous integration, continuous delivery practices are basically about that: shifting things left, evaluating them as early as in your pipeline as possible. And ideally, you would want to learn to code things knowing that no one will check them after you and they will go directly into production. That's how you should try to work as an engineer, without expecting a safety net of testers working for you and relying on the safety net of your unit integration, basically the whole pyramid of tests you create. And of course, the very basic one, always think about unhappy paths in your code. Think about what will happen when you have wrong inputs, something is not available, you have a timeout in your API call, etc. Your code should account for that, for you to have the actual quality in your software. The next piece is pretty small. We, of course, love to write code, but we should try to minimize that. The most reliable code is obviously the code that was never written, right? So always before trying to build something, try to avoid to reinvent the bicycle and try to find some solution to configure and embed into your system. We in the engineering industry, we are constantly increasing the level of abstraction of things that are ready-made and available to us. We started with assembly languages and machine code, then we build layers and layers and layers of abstraction to simplify our job. And now these layers of abstraction reach all the way up to SaaS systems and ready-made frameworks and products we may embed to build our own technology. And we should do that. We should never rewrite things that are already written for us, because this will just, again, decrease the efficiency of your production process. You will produce less for more cost with lower quality, most likely, than people who, for example, spent, I don't know, many years building some solution that you can just use. So that's the thing about writing less custom code. Of course, you will have to write some custom code anyways, because if you do not write some custom code, there is no unique value in what you are creating. You're just using pieces already existing. So there will be always some custom code, but you should avoid that at all costs where possible. And the last one, this principle is basically the general concept that you may see pieces of this concept basically in every other principle I mentioned, and we are talking here about a concept of feedback loop in a system, systems thinking, in a systems theory. So basically, it doesn't matter what system do you have. In our case, we have a system of people producing software, which is an engineering team. What's important to understand is that this system, the analog of this system is not a manufacturing system. We are not a conveyor belt of producing software. The analog is a learning system. So I would argue that what we are doing when we are creating a new product, we are basically we can think about product as something that exists somewhere. We just doesn't know, we just do not know how it looks like, how this product looks like. And what we do when we work in a software project, we uncover this product piece by piece, piece by piece. We learn something and we understand how to better build this product. So it's continuous learning process. Learning works the most efficiently when your feedback loop of this learning is fast, it's short, which means that, for example, when you're writing a code, if let's say to understand whether your code works correctly, you have to upload this code to some server, and then only then you can launch it and see if it works. You would spend, you know, days, weeks to build something useful. On the other end of this spectrum, when you have your IDE, and if you type some wrong, syntactically wrong code, it will immediately within milliseconds highlight this code to you. This is your short feedback loop. And since this feedback loop is very short, you very quickly iterate on the, for example, syntactically correct code that you are producing. And to learn faster, you should always aim to reduce this feedback loop, find a way to get this feedback faster. It's true for technical work, like if something to reproducing some bug takes you, I don't know, a couple of minutes, try to find a way to do it within seconds. If your tests you'd build for an hour, find a way to build it in minutes. This will increase the efficiency of the whole team. If you are building some feature and you wait for a week to show it in the demo, you're potentially wasting a week. Try to find a way to work with daily even cycles with your end users to shorten this feedback loop. So always try to find the way to shorten this feedback loop. It will increase the efficiency of your learning, and this in turn will increase the efficiency in how you produce the product that you engineer. So that was the last one. And for those interested in why these things work, so there are 3 books I would recommend to read about. So these are the fundamental ideas we use in building our processes and defining these principles. So you can read more deep explanations here. So yeah, that's about it. Now we have some time to use for Q&A. So let's just jump into that.
Yeah, thank you, Paul. I see we have questions already in the chat, but before I read that, I really want to ask you, so people would have time to write some more questions. So now we know the theory, right? But what is the next practical step every person on this call can take to start integrating all of those principles? Like, should it be changing your mindset, reading a book? What should it be, in your opinion?
Just take the smallest piece of this that you understand and just start doing that. I would say that for me, the most revealing step was starting to start talking directly to people I produce software for. It's very easy to be in the bubble of we are great engineers, we are producing great software, and those pesky users, they just do not know the value of this software. So to avoid that, start talking directly to people you are working for, producing software for, and create things that are genuinely useful for them, not for you.
Great. This is actually a great hook for our next speech. But before I present our next speakers, let's answer some questions. So the first one comes from Mikhail. What is the difference between the first principle, engaging the end user, and the last one, continuous feedback loop?
The first principle is a specific case of the last one. So the last principle, as I mentioned, is the most general thing, and this is a concept from systems theory, increasing shortening the feedback loop for any system increases the efficiency of this system in delivering what it needs to be delivering. And you could argue on such high level of abstraction, you could argue that every principle is basically a specific implementation of this feedback loop. So yeah, you are correct. It's a specific case of the feedback loop. And the continuous feedback loop is the most efficient feedback loop.
Cool. Mikhail, if you have any more comments on that, just put them in the chat. And now we'll cover the second question from Ales Kutepov. So there's a big comment and a question in the end. So yeah, let's listen closely. Bugs in code are the result of wrong realization of expectations. To decrease the amount of bugs, we should increase the observability of the system, which includes logs, metrics, errors. Did I catch it correctly? If so, are there any other approaches that will show us how close the realization is to our expectation of the system, except logs, metrics, and errors?
Yeah, great question. Logs, metrics, and overall concept of observability, this is a reactive concept, which means that problem already happened, and these things help us to solve this as soon as possible. Because if you do not have even error logs, you of course would have very hard time fixing something, reproducing it. So observability is a reactive thing in terms of bugs. Proactive thing is test-driven development. So spend a little time here explaining. So why test-driven development is important, and specifically test-driven development and not just producing tests after you produce the work. So as I mentioned, the defect, what is a defect? It's a difference between someone's expectation, how things behave, and the actual reality of how the things behave. Why this happens? Because once we start producing code, we write dozens of lines of code, and these lines start interacting with basically we have an exponential explosion of different combinations of how things work with each other in a large system. We cannot predict in our brain all the possible combinations. That's why we start having basically blank spaces and in understanding of how certain pieces of system, a large system specifically, might work. So what do? We produce self-testable code, self-diagnosable code, which means we write code in such a manner that guarantees us that it works as we expect. Now, how do we do that? We capture our expectations, and we capture our expectations as tests. That's why it's really crucial to write tests before you write the system, because in this case, you are basically guaranteed to produce the code that covers your expectation. It still may be the case that you didn't capture some of the expectations correctly. In this case, you once you fix the defect, you basically add something to a suite of your tests. But once you start with tests, this will first of all help you to produce better code design, because you will be practically forcing yourself to produce diagnosable code. If you do not write tests first, chances that you will produce the code and this code will exhibit some behavior that's not diagnosable. For example, you write a function and then you realize that, okay, the way I structure the interface of this function doesn't allow me to write a good test. So now you refactor the function and create this test. If you would write the test in advance, you would never write the function that is not testable. You would have to write it in a testable manner because you already have a test. So to prevent bugs, use TDD. To solve bugs retroactively, use observability. You need both, and yeah, proactive correction and is for TDD.
Cool. Thank you so much for an interesting question. That was long and really comprehensive answer. So I can't see any more questions in the chat, so I guess we can move on. Thank you guys for the questions, and thank you for Paul for your presentation.